Hello everyone, this is our last topic for exam 4, topic 17, non-elementary integrals. And we refer to them as non-elementary integrals because they cannot be evaluated by standard techniques that we've developed. And for example, sine of x squared. It looks like a pretty simple integral. If you wanted to put some parentheses around the x squared you could, but it's not necessary. But the x squared is the argument that belongs to the sine function. Imagine what you try here. Basic u substitution fails for the sine of u because the derivative of x squared is 2x, and in differential form 2x dx, but there's no x in there to help satisfy the du. So therefore, since there is no method of integration that will work, the only thing we could do is basically approximate this integral. And here we're asked to do so with a magnitude of less than 10 to the negative 8th. So to see how pretty small decimal number. But in any event, here's the hint. What we're going to do is, as we did in lesson 15, we're going to use substitution. And the fact that we know what the sine of x is, to turn the sine of x squared into a polynomial. And I included summation notation here, but really not necessary. We're not concerned about that. We just want the terms of the polynomial. And if we could turn this function into a polynomial, which now we know we could turn any function into a polynomial by Taylor and Maclaurin series, then we will be able to integrate it, because obviously a polynomial is the friendliest type of function that you can encounter. So we gave the little hint here to use substitution and this primary formula for the sine of x to first find the sine of x squared, and then we're going to integrate. So our substitution. Right, so the sine of x squared means wherever we see an x in this polynomial expression for the sine of x, we're going to replace all of these x's by x squared. So we have, I'll write it x squared to the first. Here, let me even make it real fancy. Color-coded and everything. And then minus, put an x squared in for x here. We get x squared quantity cubed over 3 factorial plus next term x to the 5th, but x is x squared, so x squared to the 5th over 5 factorial minus next term x to the 7th over 7 factorial, but x is x squared, so x squared is a quantity to the 7th over 7 factorial, and so on. It's not an equals, it's supposed to be a plus. Okay, so let's do the obvious and simplify. So we get x squared minus x to the 6th over 3 factorial, because when you take a power to a power, you multiply the exponents, of course. X to the 10th over 5 factorial minus x to the 14th over 7 factorial, and so on. Now, as we saw with the binomial series in the last example, the more terms we pick up, the closer our approximation is going to be. And I promise you that the amount of terms that I give you, because this is always going to be a given, the expression for the primary series, the amount of terms that I give you in the polynomial is going to be sufficient to come within that desired error. So this is the expression now that replaces the sine of x squared in this integral. So now we could say that the integral from 0 to 1 of of the sine of x squared is the same as, well, it's the same if you had an infinite series. I mean, if you took it out infinitely. But in terms of the approximation, x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, and so on. That's all with respect to x. Okay, so now we have a polynomial, and so we can integrate this polynomial. So that becomes, here, let's continue with parentheses for now. It becomes x cubed over 3 minus x to the 6th integrates to be x to the 7th over 7, now joins the 3 factorial, multiplied of course. X to the 10th integrates to be x to the 11th over 11, which joins the 5 factorial, minus x to the 14th integrates to be x to the 15th over 15, which joins the 7 factorial, and so on. That's all evaluated from 0 to 1. Okay, so now by the fundamental theorem of calculus, upper limit goes in, so 1 goes in for x. So 1 cubed over 3 minus 1 to the 7th over 7 times 3 factorial plus 1 to the 11th over 11 times 5 factorial minus 1 to the 15th over 15 times 7 factorial, and so on. And now minus the lower limit goes in. And typically we design these to be a little bit user-friendly so that the lower limit is always chosen to be 0, because then no matter what this polynomial is, even if, I mean, obviously x is a factor of every term in the integrand, and therefore it's a factor of every term in the antiderivative as well. But even if the first term were a constant, when integrated, you're going to pick up the variable of integration. So in the antiderivative, even if the first term is a constant, there'll be an x here. So therefore, when you plug in a 0, since every term contains x as a factor, you're just going to get a big 0. So there's no need to show the substitution for that. Alright, so now it's just a matter of grinding down the arithmetic. Let me express this as 1/3 minus 1 over, maybe you want to actually evaluate 7 times 3 factorial, which is 7 times 3 factorial 6, so 42, and then plus 1 over 11 times 5 factorial is 120 times 11, 1320, minus 1 over, okay, 7 factorial is a big number. Let me see. Oh, 5,040. Let me double check that. I knew that. I don't know why I doubt myself, but let me check. Yeah, 5,040 times 15 is 75,600. And if you wanted more terms, just add them on. Okay, and then if you want to go right to decimals, or if you want to just combine those, I would probably suggest just using your calculator at this point. 1 divided by 3 minus 1 divided by 42 plus 1 divided by 1320 minus 1 divided by 75,600. So just because we are fine with decimal approximation, no use doing each one separately and then adding them. You could do that within the context of one line on a calculator or one sequence of operations, however your calculator works. And so we're going to get point, and obviously check my arithmetic here, 0.310268 158 is what my calculator shows. And that does go on and on forever, but probably, and it does repeat because they're fractions. But in any event, now times 10 to the negative 8th would be the 8th decimal, 1, 2, 3, 4, 5, 6, 7, 8. So we want to round to where the 5 is. So 0.310268 and the 5 becomes a 6. Okay, so that's it. That's the end of exam 4. So check Blackboard for announcements as normal. Check your T-Wolves email. So I'll be sending you something there as well with the exam, but the exam's going to be posted in Blackboard as well. But check your T-Wolves email for some guidelines and how to take the exam. And so we do have 2 topics left in the course that will be on the final exam. You won't be tested on them separately until the final exam. So pay attention to the announcements again and the emails that I send you. We're going to be looking at parametric equations and polar coordinates, and those are the final 2 topics in the course. So we're getting close. And check your emails for the exam 4.